My name is Mauro Cettolo, and I'm going to present the paper Lexical Modeling of ASR Errors for Robust Speech Translation by Giuseppe Martucci from the University of Trento, myself, Matteo Negri, and Marco Turchi, my colleagues at FBK. Our work regards speech translation, the task of automatically converting utterances in one language into text in another language. There are two main approaches to speech translation, namely the well-established cascade approach and the more recent direct approach. We focus on the cascade approach, where first an automatic speech recognition system transcribes the utterance, and then that transcript is translated by means of a machine translation engine. One of the main problems of the cascade approach is error propagation, that is, the fact that transcription errors corrupt the input of MT, which therefore generates inaccurate translations not only because its own weaknesses, but also for mistakes of previous stages. Efforts made by researchers for avoiding error propagation can be grouped into two classes. The first class includes the solutions for a tighter integration of the ASR and the MT modules, which is implemented through the generation of multiple transcription hypotheses instead of the single best, like n-best, lattices, and confusion networks. The second class includes solutions for making the MT model robust to ASR errors. This can be obtained by injecting ASR errors, either real or artificial, into the source side of MT training or adaptation data. Our work regards the synthesis of artificial errors. The idea is to model the noisy channel for transforming a correct transcript into an ASR output. First of all, as usually done, we need the probabilities of the three types of errors, that is, insertions, deletions, and substitutions. The novelty we propose is that for each word we collect the set of possible substitutes and the corresponding probability. In a similar way, it is possible to model insertions through the probability distribution of the empty word. Error and distribution probabilities are used for transforming word by word a correct text into an ASR output by using the algorithm defined by this finite state automaton. The probabilities are estimated using the Levenshtein-based word alignment between an actual ASR output and a reference transcript. Once the model is available, it can be applied to any text. Let's see how it works in practice. The goal is to transform a correct English sentence into a plausible ASR output. Consider the first word. Let's roll the weighted die to choose the operation to be applied to it, and suppose that the die says to keep the word as it is. Then the word is then simply output. Let's roll the die for the second input word. Let's suppose that this time the die says to delete it. The output remains unchanged. For the third word, the die says to keep it, and therefore it is appended to the output. The same for the fourth word. For the fifth word, the die says to replace it. For selecting the substitute, we consider the probability distribution of the word recognized. We roll another weighted die and let us suppose that the choice falls on the word rec, which is so appended to the output. For the last input word, let us suppose that an insertion has to be performed. This time, we have to work on the probability distribution of the empty word. We roll the die and the word A comes out. It is appended to the output, and again we consider the input word speech, since performing an insertion implies to remain in the same state of the finite state automaton defined in the noisy algorithm. Let us suppose that the new operation is another insertion. This time the word picked up from the probability distribution of the empty word is nice, which is appended to the output. The input word speech is then processed for the third time. Let's suppose that the die rolling says to substitute it. The probability distribution of speech is considered, the word beach is chosen and appended to the output. The processing is so over. We have just seen how the input sentence, "it is hard to recognize speech," can be transformed into "it hard to recognize speech" by our algorithm. Of course, the probability that exactly that transformation happens is low, and many other outputs are possible. But since the algorithm uses probabilities estimated on real ASR transcripts, strings that look like ASR outputs are more likely to be generated than others. As said, the algorithm can be applied to any amount of text. In particular, we apply it to the source side of bilingual texts that are used for training or adapting empty models. The same correct target is paired both to the correct source and to a text which appears as it had been generated by a speech recognizer. This way, the empty model hopefully becomes robust to ASR errors. Here are some results presented with more details in the paper. They regard a speech translation English-Italian test set in the news domain. We measured the blue score of the translations of automatic transcripts generated by two very different ASR systems. We can see that the use of the lexical distributions improves the score of our starting empty model by 2-3 blue points, definitely higher than the improvement got without the lexical component. Note that our robust empty models have been adapted to an amount of artificially corrupted data which would correspond to an ST corpus of about 6,000 hours of audio, resource that simply does not exist. Instead, here are some results which are not included in the paper. They regard the publicly available benchmark EuroParl-ST, and in particular the test set of 8 languages paired with English in both directions. The order rate of the automatic transcriptions ranges from 9 to 17%, with an average of 14. We adapted the generic empty models on a combination of real and artificial ASR errors. The blue scores improved by about 2.5 absolute points, on average, but without big differences between languages, showing the portability and scalability of our method. In summary, in the ambit of the cascade approach to speech translation, in order to make the empty model robust to ASR errors, we propose a lexical noisy model for emulating ASR errors. Artificially corrupted data generated by our model have been proved to be effective in different domains and conditions. Moreover, our model is not too demanding in terms of training data and is quite domain and ASR independent. On the other side, it relies on two false assumptions. First, that words in noised text are independent from each other. Second, that each of them originates from a single correct word. The impact of these assumptions should be further investigated. Thank you for watching.